Well, howdy everybody. It is late in the evening here at UT campus, and we are going to talk about principal component analysis for dimensional reduction and for inference, understanding the structures within our data that we're working with. Last time we had a discussion about machine learning. We talked about fundamental ideas of machine learning, inference and prediction, supervised, unsupervised. And so today it makes sense to start talking about a very simple method for unsupervised learning. How do we learn from our data? And so that's principal components. And so what's the driver here? Well, the driver is that we deal with a lot of variables. We have fundamentally multivariate problems to deal with. Now, one of the definitions of big data is variety, that you have a lot of different scales and data types all mixed together within one data set that we need to work with. We have that, and it's gotten worse for us. Traditional reservoir modeling workflows were pretty bivariate, usually two variables at a time. Facies, and then you had porosity within facies, and permeability constrained by porosity. But it's become more complicated over time. We need to start accounting for relationships between multiple variables and do a better job. And part of this is driven by unconventionals and whole earth modeling. So with whole earth modeling, we're trying to close the loop. We're trying to run forward seismic on the model. So now we've got to model these seismic elastic properties and so forth. So with unconventionals, we're being driven to look at a lot of different variables. We're trying to understand flow, and so we're talking about fracture properties, fracture densities. We're talking about the traditional facies, permeability, porosity, and so forth. We're talking about geomechanical properties, the brittleness of the rock and so forth, the geophysical properties, as I mentioned before, and things like total organic carbon, the maturity of the rock measured by maybe vitrinite reflectance. There's a lot of different variables we have to look at. We have to deal with multivariate problems. Now, with working with multivariate problems, it's challenging. Visualization gets harder. Imagine a three or trivariate situation. Well, you've got one variable, second variable, and then you can color code the points to represent the third variable. Now, what about 4 variables, 5 variables, 10 variables, 20 variables? It gets very hard to visualize what's going on, to understand the data structures. It gets harder and harder to detect patterns, to form predictive relationships, and so forth. And so this gets harder. And so we're motivated to consider the option of dimensional reduction. Dimensional reduction is all about taking your variables that have m variables, your problem that has m variables, and transforming it to a representation that has fewer variables needed. Now let's think about why we'd want to do that. If you have features 1 through m, that would require m choose 2, or 2 times m minus 1 divided by 2, individual scatter plots to describe the relationships between all the possible combinations of those variables. And now consider that that's just the bivariate relationships. If you've got a 10-dimensional data set, what about the trivariate? What about the 4 variable at a time, the 6 variable combinations at a time? It gets harder and harder to be able to understand the data the higher the dimensionality. And so also remember the curse of dimensionality. What did it tell us? It told us that we need more and more data to have reasonable level of coverage as we go to higher dimensions. Well, we have a problem with having enough data available to us all the time. And so not only visualization, but even sampling becomes a problem when we're talking about high dimensional problems. One solution, go to a lower dimensionality, p, where p is less than m, where m was the original number of variables. What's the benefit? Data storage and computational time. If you have a database with 6 variables and you can cut it down to 3 dimensions or project it to 3 independent variables, that right there will cut your data size in half. Your load times, your write times, everything's faster. Visualizations, lower dimension, you can just look at it. 4-dimensional problem, if you can get it down to 2D, you can just scatter plot it. It's very easy. And it also takes care of multicollinearity. And we'll talk more about that, but let's just define multicollinearity since we mentioned it. If you go to Merriam-Webster Online Dictionary and you look it up, you'll find out that it tells you something about a high degree of correlation between supposedly independent variables. So in other words, there's a lot of information shared between the variables. If you tried to draw that, imagine a three-dimensional problem, 3 variables. One of them is in this direction right here, the other one's in this direction right here, and I'm trying to fit a surface. So the third axis is coming out of the page. I'm trying to fit a surface to those data. We're predicting the third variable with the first 2 variables. Now, if these 2 variables that I'm using as predictors for my response, which is the third variable, if they're highly correlated with each other, they are very close to each other, they're not really sampling the entire available space. What happens here is that I can fit a wide range of different surfaces, and it would be very sensitive that if I change the data just a little bit, if I move around one of these data points just a little bit, that surface could spin quite a bit. It could move quite a bit around that axis. And so that means that when we're trying to fit a model, like fitting a plane to predict the third axis, it becomes very unstable if we have things that are multicollinear. Their variables are not really providing independent information to understand the behavior. In statistics, we could describe multicollinearity as basically being a case where one of the predictor variables could be described as a linear combination of the other predictor variables. In other words, you think you have 5 variables, but in fact you have 4 variables and a variable that could be described as a combination of the other 4. You don't in fact have 4 pieces of information anymore. And that's a problem. That's a problem. It makes your model unstable, as you could see from that surface example. So let's talk about principal component analysis and what exactly it is. Let's talk about components or ideas. It is an orthogonal transformation. So what does that mean? It's like a rotation. We're going to convert a set of observations into a linearly uncorrelated set of variables known as principal components, which are all going to be linearly uncorrelated with each other. They're going to be orthogonal to each other. The number of principal components you can calculate from a given data set is going to be the minimum of either the number of variables that you're working with, m, or the number of data minus 1. And that makes sense. If you have enough data, yeah, you can find principal components, you can fit them for all of the possible variables. If you only have 5 data, you very well can't fit principal components in 5, 6, 7 variables because you just don't have enough data to be able to explore and understand those relationships. That's space. The components are ordered. The first principal component is going to be the largest possible variance described. So that one principal component does the best job describing as much variability as possible. The next principal component is going to describe the largest possible amount of the remaining variance. And the next one, the next one, the next one, to the last principal component, which is just going to describe whatever variance is remaining. Now, there might be some of you out there who are thinking, well, I thought there was eigenvalues and eigenvectors linked into this. Yes. If you go ahead and calculate the eigenvalues and the eigenvectors for the data covariance matrix, the eigenvectors will be the principal components, and the eigenvalues will be the variance described for each one of the components. Now, this is out of scope, and we're just drawing a linkage, providing a little bit of context here. I would prefer to, given those principles or concepts, let's go ahead and show you visually what this looks like. My apologies, this figure, I lost the acknowledgement or the link to the website with it. If anybody knows where this came from, go ahead and message me and I'll give credit in the comments for it. My apologies. So, now imagine we're finding mutually orthogonal projections in order of greatest variance to lowest variance described for this data set. We have 2 variables, x and y. This is the projection of the data on x. This is the projection of the data set on y. If you calculate the variance of the projection on x, you will find that it has a variance of 1. In y, variance of 1. That's because these 2 variables have been standardized so that they are centered on 0 and have a variance of 1. You'll see later we have to center on 0 every time, and we'll make a choice of whether or not to do a scaling. But in this case, we we are dealing with variables that are in fact originally have a variance of 1 and a mean of 0 each one of them. Now, if you can see the data points right here, and I could rotate a vector around that center point right here, and I could find the line for which if I project the data onto that line and calculate the variance of that projection, I maximize the variance. And if you look at the data configuration, it makes sense that it's something like here. It might be like here or what, but it's going to be in this direction. It's clear that it's not going to be in this direction to maximize variance. And if you look at the data projected onto that blue vector and you calculate its variance, you'll find out that it's going to be 1.78, much larger than the variance that we saw in the original variables x and y. So we now have a first principle component that has expressed or maximized the variance of the data along that component. Then, because we have a two-dimensional example, we can calculate, and we have enough data, we can calculate a second principal component. And we are constrained that it must be orthogonal to the first principal component. It has to be linearly independent from it, and so it will go in this direction right here. Well, if you project the data onto that component, you'll find out that the variance is only 0.22. And so there we go. In our two-dimensional problem, we now have two principal components. The first one has the most amount of variance, and the second one has the remaining amount of variance. And you can see now that, in fact, this is like a rotation. It's like we're taking and applying a rotation within the data set, and we're doing it to maximize the variance in the first direction versus. And so now, if you think about it, it's like we're fitting an m-dimensional ellipsoid to the data. We're calculating the length of this axis of the ellipse is going to be the amount of variance described by each component. So we have a lot of variance described here, not as much variance described in this direction. And so we could at any time decide to just omit one of the axes. So we take our u vector here, our first principal component, the data projected here. If we were to set the second principal component score to 0 and say that we don't want to consider any of the second principal component, this right here would be exactly what we would see. We would just see the data along that axis. And that's basically all we would see, and we would not have any of this variability, and that might be a pretty good model because we describe most of the variance. Let's talk a little bit more about principal components. One good way to do it is talk about matrix notation. And in matrix notation, we have the original centered data. So for each one of our variables, 1 through m, we've centered and subtracted the mean of each one of the variables. We apply it to a factor loadings matrix, which is right here. That's going to be our orthonormal matrix with all of our principal component loadings. And when we do that, we will get a principal component. The principal components, I should say. And so what are they? So the first principal component would be a set of features x1 through xm is really the normalized linear combination of the features. So taking these principal component loadings and applying them to each one of the variables in order to calculate this first principal component. And it will describe the largest amount of variance possible through one of these components. The normalization requires that these component loadings, the sum of them for each one of the principal components over the variables, the sum of the square of them will be equal to 1. As a result, this transform is effectively a rotation. It preserves distances. It's not skewing or messing up any of our distances. Now this factor loadings matrix would simply be all of these coefficients ordered by over all of the principal components for each one of the variables in the columns. And so this would be a square matrix with each one of those. We can calculate the first principal component score by simply taking each one of those loadings and applying them to the actual data value for each one of the data I through n. We just apply these factor loadings to each one of the variable values, and we'll get the associated first principal component score for data number 1, data number 2, and so forth and so on. And so we can do that and repeat that for each one of the principal components. For the first principal component, we would use the component loadings associated with that first principal component. As you can see here, these are all related to first principal component. For the second principal component, you use the loadings associated with the second and up to the kth. And so this is pretty powerful because we can now imagine that we can look at these principal components within our loadings matrix, and we can look at them and see what are their values. You can specifically check if maybe for the first principal component, maybe the loadings are very high for maybe the first two variables, but they're low or near zero, I should say, for the others. That tells you that first principal component that describes the most amount of variance is related, or it uses information most from those two first variables. And so it tells you something about how individual variables influence different principal components and how they're perhaps related to each other and related to the variance. Do they work together for one principal component? Are they not involved in another principal component? And so forth. In fact, for some problems, you might find some very natural groupings occur. You might find out that when you do principal components on various variables for your reservoir, that principal component 1 is mainly composed of heterogeneity type variables, permeability, porosity, so forth. While principal component 2, maybe it's mainly related to information related to completions, more or dynamic engineering information, and so forth, not the static heterogeneity model. So we can go ahead and explore and look at those principal components and try to understand the factor or the component loadings matrix to see if they have specific patterns. That's part of inference. Now, how do we do dimensional reduction given the fact that we've just calculated these principal component loadings? We have a matrix V with all of them. Well, what we need to do is we're going to take and convert our data set to principal component scores to the actual principal component arrays. If we retain all of the K components, we're not going to achieve any dimensional reduction. When we transform back to the original data, it'll be exactly the same as we had before. We gain dimensional reduction when what we do is we only retain the P first set of principal components. If we have a problem with 6 dimensions and we retain 3 principal components, we'll take the first, the second, the third, and we'll leave out the 4th, 5th, and the 6th because they describe the least amount of variance. They're the least useful components to us. So what are we going to be doing? Well, the principal components are calculated by taking the loading matrix and applying it to the data. But the cool thing about our loading matrix is that it's orthonormal. It's orthogonal. And so what does that mean? It means that its inverse is equal to its transpose. And this is super cool because if we're thinking about how do we go back, we would have to take the inverse of the loading matrix and apply it to our principal components to get an estimate of the data with reduced dimensionality. Well, super simple. We just take the matrix transpose, apply it directly to our principal components, and we will get an estimate of the data. What does it look like? We would simply take, for every one of the data values, we can calculate it simply as a combination of each one of the principal component scores for 1 through P variables applied to the loadings for each one of those principal components. And if we do that, we apply that, we will simply get back to a data value estimate with reduced dimensionality. And so this is powerful. This is super easy. I mean, super easy to see that it's very valuable because let's take a look at this right here. We got a graphical representation. Here's the reference for the figure that I showed there. 2-dimensional problem, one variable, the other variable. We calculate the first principal component. It's represented along this line right here. We go ahead and we take that summation, but we only sum 1 through P equals 1s. We only take the first principal component. What does that effectively do? It's like we're saying that the principal component 2 score is equal to 0. It has no influence. So we are projecting the original data, these circles, onto the first principal component. If we retain only one principal component, we can only represent things on this line. And so our reduced dimensionality problem that now is representing as much variance as possible is going to be these blue circles represented on this one principal component. So I put together an example of doing principal components analysis within R. This example will be the basis for the course notes for the remaining of this discussion. I have also put together in Jupyter Notebook a principal component example, the same example with a little bit of a different spin and some different ideas in Python. And so if you want, you can check that out. I will introduce that at the end, but for now we'll look at the R example. I provide a multivariable, or a multivariate, I should say, data set with 1,000 wells, 1,000 data points, n equals 1,000, porosity, log transform permeability, acoustic impedance, brittleness, TOC, vitrinite reflectance, and production. The file name is unconventional or MV multivariate. It's a comma delimited file that can be loaded directly into a pandas data frame in either R or R or Python, excuse me. Here's the first 7 lines from the head command, and you can see in fact what the data file looks like. But of course, we can do a matrix scatter plot very easily with an R or Python. Look at all the different various relationships between the variables, 2 variables at a time. Pretty useful. You can see some curvilinear features, some heteroscedasticity, definitely some complicated kind of nonlinear features going on here too. And you can look at it. Now, what we'll do is we'll go ahead and take 2 of the variables out. So we have log transform permeability versus porosity. Here's the relationship right here. We just take the first 100 wells for ease of visualization. We don't want to have too dense of a data set to work with. And we'll go ahead and we'll try to do some principal component analysis on this. First thing we're going to do is we're going to run and calculate the principal components, the loading matrix. Here's the loading matrix. Principal component 1, principal component 2, variable porosity, variable log perm. And so we can look at the loadings directly. What do we see? We see that the majority of the weight, the highest absolute value for loading, for principal component number 1 goes to porosity. And then the second principal component seems to be dominated by log permeability. They're separated pretty nicely. That works pretty nice. We can calculate the principal component scores, transform our data from the original porosity to principal component scores simply by taking for principal component score for data value number 1. So we're going from I equals 1 through n data values. So principal component score for the component 1 for data I is equal to the component loading for porosity for principal component 1, multiplied by the porosity data centered, we're subtracting out the mean, plus the principal component loading for log permeability for the first principal component, applied to log perm minus the mean of log perm. And we can do this for principal component number 2, repeat down there. And in doing this, we have mapped the original variables into a principal component scores, where principal component score 1 is going to describe as much variance as possible. My apologies, in the notes here I switched from I's to alphas, but use them interchangeably on this slide. I should have caught that. My apologies. So let's look at what that looks like, that transform. So we take the original data, porosity, log permeability, and we are transforming it to the principal component scores for principal component 1 and 2, and we plot it. What do we see? What does it look like? Well, it's very interesting because if you look at the data, look at these 2 points here, look at these 2 points here, look at the 3 points here, look at the 3 points here, 3 points here, 3 points here, I can convince you that this is really mainly a rotation where the principal component axis of component number 1 probably went like this, and we rotate it, so now we see the principal component 1 aligned with this axis when we look at the scores. There's also a bit of an expansion, and that's because we do some normalization on the variables, and so it causes this kind of expansion on them. So we can go through the whole workflow for dimensional reduction. Let's show it to you right here. We identify principal component 1, principal component number 2. They're represented by the factor loadings. We apply the factor loadings, or the component loadings we can call them, in order to transform to principal component scores. Principal component score 1, principal component score 2. We can remove the second principal component by just setting all of its principal component scores to 0. Effectively, we're just taking the summation of 1 to p, and that p is now equal to 1. We're ignoring component number 2. They're effectively going to be like they're 0, and so we collapse everything onto the first principal component. There's no thickness here anymore. There's nothing in principal component number 2. We inverse the principal components by taking the principal component scores, and we go ahead and we do the reverse by using the transpose of our V matrix with our component loadings. We would also recenter the data because we actually had to subtract the mean out, and if there was a rescaling we would count for that too. And we're back here in the original data space, same data space, but now we have a reduced dimensionality model. We can describe the porosity log permeability relationship with a single variable along this axis. And so our problem's gone from 2D to 1D with this principal component. So that's pretty powerful. Now, biplots are another a diagnostic tool that are commonly used with principal component analysis. The idea with a biplot is we want to visualize the data in the principal component scores and the influence of each one of the variables with regard to this model. And so the way we do it is the first part of the plot, if you look at it, is effectively the same thing that's in this plot right here. The only difference is we're going to go ahead and we're going to label each one of the data values with the number index or some type of unique identifier. Why do we do that? Because if there's a certain values that don't seem to make sense in the principal component score space, you can identify them, look at them, and see if there's a problem with them. Then what we can do is we can take the component loadings for each one of the variables and we'll plot a vector going from 0 to the component loadings in the principal component 1 and 2 for the variable porosity. We do that for log perm. If we had a bunch of variables, we do that for each one of the variables. What do we see? Well, if we look at this problem right here, after we have standardized centered it for sure, but maybe standardized it, you see that porosity, log permeability are really equally sharing the contributions to each one of the principal components. Each one of them is equally influencing each one of the principal components. That's the message. That's probably after a standardization that you see that. Now, since I mentioned standardization or scaling for the purpose of principal components, let's define that and talk about that a little bit more. You are trying to find the independent principal components in the order that describes the most amount of variance to the least amount of variance. So we're interested in decomposing the variance of the problem into these principal components. Now, think about this example right here. You could have porosity versus permeability. So we got permeability, we got porosity here. Now what could happen is, what if you take permeability and you change it from millidarcies to darcies? You're effectively taking your permeability values and you're applying a scalar of 1/1000th. You're dividing them all by 1,000. We remember from our discussion about expectation and variance that if you apply a scalar to a variance, that in fact that you would have to take the square of that scalar to see how it, so that's a huge impact on the variance overall. Okay, so, but by doing that, you'll dramatically change the principal components because suddenly permeability will be the most important variable to apply on the first principal component. Clearly, it describes the most variability. Well, we don't necessarily want that to happen. We don't want the units of the problem to matter. We want to make it independent, robust in the face of change of units. So, what do we do? If the variables we're working with are different things, they don't have the same type of units, they're not consistent with each other, it's probably better to standardize. We're going to center the variable. We always center it. We have to center it. But we're going to standardize it so each one of the variables has a standard deviation equal to variance equal to 1. That way we remove the influence of the spread of each one of the individual variables from the principal component analysis calculation. Now, if your variables, in fact, are of the same unit, they are the same thing, then maybe they're a grade concentration, different mineral concentrations, so the units themselves are important and they're meaningful across the different variables. They're not just distinctly different things thrown in together. Then perhaps you're concerned about the influence of the range of each one of those variables. You want to account for their variances and they're meaningful with regard to each other. In that case, you would not want to do any scaling. You'll work with the variables centered without readjusting, or adjusting I should say, the variance or standard deviation of each one of them. So it's amazing, even 8 o'clock at night, I keep being interrupted by my graduate students coming to ask questions. So I'm back again. So let's go ahead and talk about how we can calculate the variance described by each one of the principal components. And so how do we calculate that? All we have to do to calculate the variance explained by each principal component is take the average square of the component scores associated over all of the data for each one of the principal components. And so we just have to take the square because they're going to be centered. So the mean is equal to 0, so that's good. And what we should find if we do that is that the variance described by the first principal component will be larger than the variance described by the second, larger than the variance described by the third. They should be monotonically decreasing as we go from the first principal component to the kth principal component that we are working with. Let's discuss just a little bit about how we can use principal component analysis to help us in prediction. Everything up till now has been kind of more focused on inference problems, talking about inference and understanding relationships between variables. How would we use it to assist with prediction? Well, we'll show that there's an advantage to working with a reduced dimensionality model for the purpose of prediction. So let's just talk about how it would be done. Well, let's compare and contrast it to regular multilinear regression. And so in that case, we would have our data, all of our predictors, which are shown here by the X array. We have the number of data available to us, and we have 1 through k predictor variables to work with, or features. And then we would apply multilinear regression in order to take those and to fit a model to predict the response y. Now, what we do with principal component regression is we will take that regular data matrix and we will apply and calculate principal components on it, and we will then be able to calculate the principal component scores for the first 1 through p principal components that we want to work with. We've reduced the dimensionality. This should be p right here, where p is less than k. So we're only using the components that describe the most amount of variance. Then we could do multilinear regression using those component scores that describe the most amount of variance with the lowest amount of dimensionality. That's great. It's great because if we work with a lower dimensional prediction, we're less likely to have overfit. If we have sparse data or not a lot of data and we have a lower dimensionality, we're less likely to be overfit. The other thing that's very cool about this type of approach is it helps us with the multicollinearity problem. Because if you think about it, these principal component scores, the principal components, are providing us with a set of independent variables that we can now model with. And so we removed the relationships between each one of the inputs into our multilinear regression model. And then we work with the ones that describe the most amount of variability. We're describing as much variability as we can with as few independent variables as possible. So not only are we getting rid of some of the issues of overfit, we're also providing a more robust model from the fact that we're not going to be dealing with or working with variables that are closely related or linear combinations of each other, resulting in an unstable result. Now, the R workflow that I've shown within this lecture is available to you if you're interested. It's pca_demo.r. There's also a markdown version of the file, and they should be available to you on GitHub, along with the data set that I worked with here, which is unconventional, multivariate, common delimited file. If you go to my GitHub account, you will find that those are available to you under Geostat R, where I have a whole bunch of different demos for different methodologies in geostatistics, statistical analysis, and machine learning, all using R. The PCA code is available to you right here. And so if you'd like to go ahead and look through that workflow, that might be something you're interested in. So here's the markdown file for it with documentation explaining every step. You may also be interested in a Python version of it. And so in the Python version, you'll have the same workflow using the same data. I've actually gone a little bit further in Python. I've actually gone as far as looking at the principal components for the entire data set, 1 through 6 variables, and looking at what happens for the bivariate if I retain a certain number of principal components, also the multivariate scatter plots, matrix scatter plots I should say, in the case of retaining 1 principal component for the approximation or estimation versus 6 principal components down here. So that's available to you if you want to see the Python. You can go ahead and see that, but coming back to Geostat Guy on GitHub and go into Python numerical demos where you'll see a bunch of demos in geostats, some standard statistics type of approaches and machine learning. And here's the PCA demo shown right there. And the data is also available to you. Well, I sincerely hope that this discussion and lecture has been helpful to you. I found a lot of my students in the lecture today were really interested by this idea of dimensional reduction and the ability to simplify complicated problems for the purpose of inference and prediction, to understand our data and so forth, to visualize them. So if you have any questions or comments, go ahead and contact me. I am the Geostats Guy on Twitter. I'm available on LinkedIn and all kinds of places. I am Michael Pyrcz. I am a professor at the University of Texas at Austin. And so I'm super easy to find. If you go to my department website, you can find, of course, my contact emails and so forth. And I welcome anyone who has questions, comments, suggestions, and so forth. All right. Take care.